Welcome to another class, everyone. At this time, we'll be taking another topic, which is energy quantization. I'm going to share my screen and we'll have a deep dive into it right immediately. So here's my screen, and we're going to start class as soon as possible. Now, speaking of energy quantization, I need to bring into cognizance some explanation first. Bohr, the one who we've been talking about in the previous lectures, Bohr suggested that the electron, let's start from there, that the electron in the atom exists in discrete, I'm going to underline this word, discrete energy. Discrete energy known as discrete, suggests that electron in the atom exists in discrete energy, let's say discrete energy packets. Now, called quanta. So we can define quantization. Energy quantization can be defined as the existence of electrons in atoms as the existence of electrons in atoms as discrete or indiscrete rather, indiscrete energy packet or indiscrete energy. Let's put it like that. Indiscrete energy which can be removed from one level to another. So the idea here is that energy exists discretely. So we have discrete energy and it can be removed from one level to another. So that discrete energy packet is called quanta. It's called what? Quanta. So that's what we stated, that energy in such discrete packets is called quanta. Or let me say energy quanta. Let's just add an energy here. Energy quanta. So yeah, let's continue discussion. So we've established some things. If we write this as a formula, we write E equal to HF. That's the formula, where H is Planck's constant and F is the frequency. Now let's discuss that energy level. Let's talk about energy level in atoms. Energy level in an atom. Electrons in atoms, in atoms arranged around their nuclei. In positions called energy level or electron shell. Energy level electron shell. Electrons in atoms are arranged around their nuclei in positions called energy level or electron shell. So take note of that. It requires more energy to remove electrons from the first energy level than to remove electrons from any other higher levels. So it says it requires more energy to remove electrons from the first. Just take note of this explanation. To remove from the first one requires more than from any other. And the formula that guides us in determining that energy is E equal to -1 over n square. So n is the quantum number. I'll put it as electron quantum number. Just take note of this formula. So n is the electron quantum number. We already established that E is energy. So we have this 13 in 13 electron volts. Let me write it as EV means electron volts. And we know that if we are converting that to joules, you divide by let me put like use 1 electron volt equal to 1.6 times 10 raised power minus 19 joules. So you use it. Then Z is the atomic number of whatever element you're dealing with, whatever atom. So take note of this and then we'll move forward. Formulas will be instrumental as we go ahead. Let's do something like the energy level diagram. And this is what it looks like. We draw the ground state, draw the next level, draw another level, draw another level, draw another level. I can wipe off all these sides. Then I pick this up and say, okay, this is E0, the ground state, E1, E2, E3, E4. These are at n equal to 4, n equal to 3, n equal to 2, n equal to 1, n equal to 0, and we call that place ground state. So this is where the energy level diagram looks like. Let me move it up. So the energy level diagram looks like this, and I can make some explanations. The ground state is the stable state or an atom corresponding of an atom, of an atom. The stable state of an atom corresponding to its minimum energy. When an atom is heated with an energetic particle, the atom is excited. An excited state is an allowed state of higher energy when where the atom is unstable. Let me explain what I'm saying with the diagram. So if I go to this diagram now, I will say the most stable state in this diagram is the ground state, this place. Now, once the atom gains energy, if it absorbs energy, it can rise. So if it absorbs energy, it can rise to this state, it can also rise to this state, it can also rise to this state. So it can also rise to any state from anywhere. Same thing. So, but this is the most stable state, the lowest one. So this ground state, stable ground state. Now, if we have stable ground state, every other excited state are unstable. That is, if it is not in the ground state, every other place is unstable. But it gains energy, absorbs, to gain energy. We've talked about this before. To rise. Then you can emit energy to fall. So if it is somewhere here now and it wants to fall to this place, or fall to this place, or fall to this place, so it emits energy to fall. You see that? Very important. So, and if it is not in the ground state, it's excited and it's in an unstable state. So that is the point. Let me establish that during excitation from lower, like we said, excitation is from lower to higher energy level. The potential energy is converted into kinetic energy so that the electrons eventually acquire a velocity of that velocity is also equal to electron volts. And what does this mean? What does this mean? This is more like, let's say, not, this is not like just the form, this is not just like a unit, this is more like charge times potential difference. So I'm going to write it as QV. Yeah. So that's it. So, and that kinetic energy can be written as, the higher energy level minus wherever it is coming from, the initial state, and that's equal to HF as well. That's equal to half mv squared now. This is equal to QV. And this, hold on for a bit. Let's take some water examples. And I can write something in between here before I go on. Let me. So this HF is also the same thing as HC over lambda, or is equal to half mv squared is equal to QV. So let me rewrite this line above so that it doesn't confuse you. I mean, I don't want it in two lines. So we said kinetic energy is equal to half mv squared is equal to charge times potential difference. That can be written as Q. Q is charge, potential difference V. So that's where we now said, okay, since this is also a form of energy, and energy can be written as the difference between, and kinetic, we said kinetic energy only happens when there is excitation. Potential energy is converted to kinetic energy. So when there's excitation, it means you move from one state initially to another state. So if you want to find the energy difference, find it by using this. That's the kinetic energy used to move. So, and that is also equal to, we know that the energy is equal to HF on what we've established before. That was right here. Right here, establish that. So we now also introduce that here. So kinetic energy equals to HF, and F is equal to C over lambda. F is C over lambda. So we just put it there. Then we've already established half mv squared from the previous place, and then we've established QV also from there. So that makes us to, make that conclusion. Now this is a valid formula. Let's take some worked examples now and proceed. Worked examples, or let's say examples. We're going to work it together. So examples. 1, the change in energy level of an electron in an atom is 6.2 times 10 raised per minus 21 joule. Calculate the frequency of the photon. The wavelength So now they gave us the change in energy level. That is, they gave us change in E, which is like E n minus E naught. They gave it to us already as this guy. And they're asking us to find frequency. Asking us to find frequency. So we know that this change in E, we can write it as HF. So that means that change in E, they have given it to us as 6.2 times 10 raised per minus 21 is equal to HF. We know that H is Planck's constant. And okay, in the question, they already gave you the constants to use. C equal to 3 times 10 to 8. And that's how they will do in most questions that relate to this. And H is, so these are constants. They'll give them to you times 10 raised per minus 34 jouleseconds. So now H is already given to us. We just plug it in right here. 6.2 times 10 minus 21 equal to 6.625 times 10 to the minus 34 and F. So F is definitely going to be 6.2 times 10 to the minus 21 over 6.625 times 10 to the minus 34. So F is definitely going to be, let me grab my calculator. Give F to you. Six point two times 10 to the minus 21 divided by 6.625 10 to the minus 34. So that will give me 9.358 times 10 raised per 12 hertz. So, and they now said, okay, that was the first part that asked us to find frequency. Now asked us to find wavelength. Wavelength. And we know that already that F equal to C over lambda. I've established that to you here. F is C over lambda. So we already know F. We're looking for lambda now. Lambda will be F C over F. So C is 3 times 10 raised per 8 divided by this one, 9.358 times 10 raised per 12. So that being established, say 3 times 10 raised per 8 that will be 3.2. 3.2 sorry, let me see. Times 10 raised per minus 5. That will be the wavelength. And wavelength is in meters. According to, because the unit here is unit of C is meter per second. So wavelength to be in meter, 3.2. So we establish that. Take another worked example. Catch your breath on this example, and then we'll bounce straight into the next example. So that's the idea. Let's take the next example. The next example goes like this. An atom excited to an energy level E2 equal to minus 12.42 times 10 raised per minus 19 joule falls to a ground level of energy E naught equal to minus 30.3 times 10 raised per minus 19 joule. That says to calculate the frequency and the wavelength of the emitted photon. So the idea here is let's analyze the parameters we are given and what we have to find. You say an atom is excited to energy level. They give us one energy level E2 minus 12.42 times 10 to the minus 19 joule. They give us ground state minus 30.3 times 10 raised to the minus 19 joule. And they ask us to find frequency and wavelength, lambda, frequency F and wavelength lambda. So now what we'll simply do is do the change in energy. And we know that change in energy is the higher energy level minus the lower one. So we say E2 minus E naught. So that will make us to, and we know that this is also equal to HF. So let's do that first. Let's do E2 minus E naught minus 12.42 times 10 raised to the minus 19 minus 30.3 times 10 raised to the minus 19 will give us HF. We already know our H constant from before. So let's do this subtraction. If we do the subtraction, we're going to have 17.88 times 10 raised to the minus 19 equal to HF 6.624. That's H. Let's go back to the last. No, 6.625 times 10 raised to the minus 34 times 10 raised to the minus 34 F. So F is definitely going to be 17.88 times 10 raised to the minus 19 divided by 6.625 times 10 raised to the minus 34. So F is going to be S bracket is 17.88 times 10 raised to the minus 19 divided by 6.625 times 10 raised to the minus 34. That will give me 2.6. No, it has to be 2.699. 2.699 times 10 raised to the 15 hertz. We also know that's the first part. That's to find frequency, and then that's to find wavelength. We know that F equal to C over lambda, so lambda equal to C over F. So C is already 3 times 10 raised to the 8 divided by 2.699 times 10 raised to the 15. So when we do that calculation, 3 times 10 raised to the 8 divided by, we get about 1. Hold on. Hold on for a bit. Oh, I see. Oh. Yeah, it was Joe. Okay, yeah, that's right. So let's just put it 1.11 times 10 raised to the minus 7. Minus 7. We'll call that lambda. That will be meter now. Let's take some more examples. Let's take 2 more, or maybe 1 more. And that will be example 3. The ground state of hydrogen is minus 26.3 electron volt, and the second state is minus 10.3 electron volt. Calculate the wavelength of the radiation if the electron returns to the ground state. So now let's establish what we are given and what we are asked to find. We are given the ground state, which I can write as E naught to be minus this, and we are given the second state to be, we have to calculate wavelength. So if it returns to the ground state, now the idea is that it returns. So this E2 and E naught, and for it to return, let's find that energy difference. Get it? So Energy difference would be the the final state minus the initial state. So energy difference is normally E final minus initial, and then it was coming to, you see the movement. So the E final here is E naught, so minus 26.3. Or better still, what you just do is don't just find energy difference. And yeah, what I'll just do is like put the modular. Yeah, put the modular sign. That is, if in case you end up with a negative, remove it. So that would be modular of minus this minus 10.3. So at the end of the day, we have modular of 10.3 coming. You know what that modular absolute sign means? It means you take out negative in your final answer. So minus 16. Now don't forget that this will now be 16 electron volt. The unit we're using was 16, it was electron volt. So when you get electron volt like this, we can't work with electron volt. Let's convert it to joule. So we know that 1 eV is this, so 16 eV will be, let's say x. So when you cross multiply, x will be 16 times 1.6 times 10 raised to power minus 19 joule. So that will give you 2.56 times 10 raised to power minus 18 joule. So that's what you get as your answer for the energy difference. But that's not our goal. We know that energy difference equal to HF. So F is our goal now, so it will be energy difference divided by H. So that's 2.56 times 10 raised to power minus 18 divided by H is already oh, our goal is not even F, it's actually this thing, wavelength. So let's use the beta formula of let's use the of we said is also equal to AC over lambda. So let's use equal to AC over lambda. So lambda will be AC over change in energy. Yeah, and equals multiply. So let me shift this. So then that would have be 6.654. Oh no, sorry, 6.625 brother. 6.625 times 10 raised by minus 34. No, it's not minus 34. Go and check it. H, value for H. Z minus 34. Hold on. Yeah, it's minus 34. So it's minus 34. So times 10 raised by minus 34 times 3 times 10 raised by 8 divided by lambda. No, change in energy now. We've already found that to be 2.56 times 10 raised by minus 18. So when we do all of this calculation, 6.625 times 10 raised by minus 34 times 3 times 10 raised by 8 divided by 2.56 times 10 raised by minus 18. I get 7.764 times 10 raised by minus 8. Hold on for a bit. Okay. Let me make sure that I did everything right there. So let me make sure that I have the me. Yeah, that's our answer. Next 10 raised by minus 8 meter. So having established that, We are going to proceed to the fourth example, which is our final example for today. If the potential difference PD by which an electron moves is 1.5 kilovolts, calculate the velocity with which the electron moves if the ration of its charge to mass is times 10 raised power 11 coulomb per kg. And then also they ask you to find the kinetic energy. So it's an interesting question. Let's establish what we are given. So we're given PD by which the electron moves. That's V, 1.5 kilovolts. That's like 1.5 times 1000 volts. That will give you 150. Am I right? No. Yes, most likely 1500. Sorry, 1500. So 1500 volts. So calculate the velocity with which the electron moves if the ration of his ration, or you can say ratio, of the charge to mass is this. What do they mean by that? If I say charge to mass, I'm saying for one mass, for one, that's meaning of per kg. For one mass, 1 kg, I have the charge Q is 1.9 times 10 raised by 11 coulomb. So now they're asking us to find the velocity. What do we need to do? Remember this formula that says change in energy, kinetic energy equal to HF equal to half mv square equal to QV. Now in order to find velocity here, we can, this is velocity mv square in mv square, but this one is volt. We establish that electron volt. That's why we said charge. If we go back to our note, we specifically said the charge times PD, charge times PD. So this is PD. This one, this V here is PD. PD, this is PD. Now this one is velocity. So having established that, let's now solve the problem. The mass we are considering here is 1 kg because that's what they gave us by using the scope of per kg. So we know that velocity, we're looking for that. We already have our PD as 1500V. We know our charge to be 1.9 times 10 raised by 11 coulomb. So now let's do half times 1 times V square, which is velocity, equal to 1.9 times 10 raised by 11 times 1500. That leaves us with V square over 2, that's velocity, equal to 1.9 times 10 to the 11 times 1500. And this is 2.85 times 10 to the 14. So V square will now be, if I multiply this one by 2, 5.7 times 10 to the 14. So V will now be square root of 5.7 times 10 to the 14. And that leaves us with velocity of 2.3 times 10 raised to power 7 meter per second. I would say it's 2.39. Yeah, let me put in 1, 2, 3, 4, 5, 6, 7. Yeah, that's 10 raised per 7. So having established that, we can now find kinetic energy simply as half mv square, or we just use QV. So we know that V is 1500 and the Q there is So 1.9 times 10 raised by 11 times 1,500. That's already 2.85. Hold on. Hold on for a bit. Yeah. Hold on. Coming. Need to establish something. Yeah. Okay. So let's just use the route of for this. If we use, let's use this route. It's 2.85 times, yeah. That's it. 2.85 times 10 raised to power 14. A bit. So that will be the answer, 2.85 times 10. So this is what we call it today, and then we'll meet in subsequent classes.